Ho, ho, ho! What's up, Super World? Another wonderful day of some Super Notes. Okay, so we are starting Unit 4, and actually it deals with Chapter 10 in the textbook to start with. And we're going to be dealing with gases. Okay, so this is Chapter 10, right? We're dealing with gases. So we already talked a little bit about gases, and remember, our gases are going to, their particle motion, they're going to vibrate, they're going to rotate, and they're going to translate. So they have this particle motion, and we're going to spend some time talking about how they translate and what's happening with these gas particles. And this is really governed, or we use what's called the kinetic molecular theory to explain this behavior of gases. We also just call it the KMT, or the kinetic molecular theory, right? So this is what we use to describe the behavior of gases. So this theory describes the relationship among pressure, volume, temperature, velocity, and frequency and force of collisions. Now, the KMT has four major ideas that we have to understand. So our first major idea of the KMT is that gases contain particles. And those gas particles are in constant, random, straight line motion. Okay, so if I have a gas particle in a box, okay, this gas particle is going to be constantly moving, so it doesn't stop. Its movement is going to be random. Okay, it's going to be random. And it goes in straight lines until it runs into something. So boom, 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 boom. Okay, so you have that constant random straight line motion. Okay, let's talk about number 2. Particles collide with each other and the walls of their container. And in the KMT, these collisions are considered to be elastic. Oops. Elastic. Now, what is an elastic collision? What does that mean? It means the energy before the collision is equal to the energy after. So no energy is lost. Now let me give you a couple of examples. All right, so if I took one of my bouncy balls, right, and I threw it against the wall, right, if that collision was completely elastic, okay, it would have the same exact amount of energy before the collision as it does after. So my bouncy ball would have the same speed, same energy coming off the wall, right? So that's an example of an elastic collision. Now, if I was to drop my bouncy ball on the floor, okay, and it bounced, if that wasn't a completely elastic collision, the bouncy ball would come right back to where it started, and every time it dropped, it would come back to the same place it started. And then that would just keep bouncing forever. Now, we know that's not what happens, okay? So the bouncy ball hitting the floor is not an elastic collision. It loses energy in the form of sound and friction and heat, okay? So that bouncy ball is not an elastic collision. Another example is, I don't know, let's say we have two balls. One moving this way, one moving this way, and they collide. So, I don't know, let's say this one has 30 joules, and this one has 10 joules before the collision. Okay? It has a total of 40 joules. All right. Now we can move around this energy. So maybe coming out of the collision, this guy has 20 joules, and this one has 20 joules. So the amount of energy that this ball has now and this one could be different, but overall the total amount of energy is the same both before and after the collision. So this is another example of an elastic collision, right? In the KMT, all of these collisions with the gas particles, either with themselves or on the walls of the container, they're all considered to be elastic. Okay, so they're not going to lose any energy. Our third major idea. There are no attractive forces between gas particles. All right, so there are no, okay, we know that in a solid, the particles are held in nice strict geometric pattern, right? And they're held together by these strong intermolecular forces, these strong attractive forces between the molecules. In gases, the kinetic molecular theory says there are no attractive forces. Okay. And then finally, our fourth one, the volume of a gas particle is negligible, extremely small. Okay. Because of this, gas particles are separated by great distances. I want to try to explain that a little bit to you. Okay. So let's say that I have two gas particles that are this big. And in this case, okay, we only have this distance right here between them. Now, what if those gas particles were this big? I still only have two gas particles, right? I just have two smaller gas particles. Okay, what happens to the distance between those gas particles, right? By just making these gas particles smaller, the distance between them gets bigger. Well, what if I reduce it even more? Okay, my distance even gets bigger. Now, when we're talking about gas particles, when we're talking about gas particles, they're extremely small. So since they're so small, there's going to be relatively big distances between them, right? And that's what number 4 is telling us. Okay, so hopefully this helps you out a little bit with number 4. Now, the KMT uses what's called an ideal gas. Okay. Ideal gases, they're not real. We made it up for the model. Okay. We made it up for the kinetic molecular theory. Now, an ideal gas, okay, follows the KMT completely. Okay, so this ideal gas would follow everything about the KMT. Right now, there are problems. Okay, there are problems with the KMT when we start using real gases. So when I talk about real gases, now I'm talking about, I don't know, O2 gas, H2O, H2 gas, CO2 gas. I mean, these are real gases, right? Now, these guys don't completely follow the KMT. It's because there are some issues with this KMT. And if we go back through them, okay, so number 1 isn't a problem most of the time. So we know that the particles are in constant random straight line motion. That's okay, all right? Number 2, okay, do you think the collisions with each other and the walls of the container are always completely elastic? Well, the answer is no. All right, it's just not possible. Now, they're close to being completely elastic, right? But they will lose a minute amount of energy, right? So real gases will not be exactly elastic. They're really, really close, but not exactly. All right, so that causes some issues. Here's another thing. Does it make sense that gas particles have no attractive forces between them? Right? Well, no. I mean, if they're attractive forces when they're a solid, and they're attractive forces when they're a liquid, okay, does it make sense that all of a sudden when it becomes a gas, there are no attractive forces? And the answer is no. So in real gases, we do have attractive forces between these gas particles. And then finally, the volume of a gas particle is negligible. All right, KMT is basically saying it's 0. There is no mass. There is no volume. But in reality, gas particles have volume. They take up space, right? Gas particles are not always separated by great distances. They go by each other because they're all in constant random straight line motion. So there are some issues with the KMT, all right, when we start using real gases. Now, we can make real gases act like an ideal gas under specific conditions. So a real gas acts most ideal at low pressures and high temperatures. So real gases act most ideal at low pressures, high temperatures. The question is why? Well, in those conditions, it helps us with some of the problems of the KMT. So at high temps, okay, we speed those particles up, so we got lots of kinetic energy. So that extra kinetic energy, it speeds the particles up. Well, that helps us with some of the problems of the KMT. Right? So for example, right, one of the things in the KMT says there are no attractive forces between these, right, and that the particles are always far apart. Well, if these are going in random constant straight line motion, they're going to come near each other. And when they're near each other, they're going to have an attractive force. If the particles are going slow, that whole time that they're near each other, they're attracting each other. But if we speed those particles up, the amount of time that those particles are near each other is reduced, which reduces the attractive force between those. So if we put these at high temperatures and speed them up, it helps us with some of the problems with the kinetic molecular theory. Now, what does low pressure do for us? Well, if something's at low pressure, that means it's going to generally have big volumes, which means we're going to spread out the particles. Okay, so remember that KMT says these particles are way far apart. So if we have big volumes, it spreads them apart, so it's going to help this act most ideal. Now, the other big thing with this has to do with that volume of that particle. The smaller the mass of the gas particle, the more ideal it will behave. So our KMT says, look at our gas particles basically have no volume, no mass, right? So that's what the KMT says. So if we use real gases with small mass, they're going to act more ideal. So atomic hydrogen, okay, is our smallest gas particle. It will act the most ideal. But if you get into big ones, like, I don't know, some of the noble gases, xenon and radon, okay, some of these guys, these are big. Okay, they're big gas particles. They do not act very ideal. Okay, so the lighter the mass, or the less mass there is in the particle, the more ideal it will behave. All right, now we're going to be using a lot of this stuff, all right, as we explain some of these gas laws as we go through them. So let's just talk about a couple things. So gases apply pressure in all directions. Well, why is that? Well, the particles are moving in that random straight line motion. Okay, so they're moving in all directions, right? So let's say that I have I don't know, a piece of paper up in the air and there's gas under here. Okay, well, these particles they're in random straight. They're going to go up and they're going to run it, so there's going to produce an upward pressure. Okay, let's say I have a piece of paper here. It's going to apply a sideways pressure. Right? And then if it's down here on the table, it's applying pressure this way. So gas particles, because they're in that random straight line motion, right, they're going to apply pressure in all directions. Now, really what we're talking about when we're talking about pressure, we're talking about gas particles colliding and applying a force. So pressure, okay, has to do with how much force is being applied by the gas particles' collisions. Now, pressure is defined by the amount of force per unit area. So pressure equals force over area. Well, where do we see this the most? Well, we see it in atmospheric pressure all the time. So our atmospheric pressure equals the force from the mass of air pulled toward the Earth's center by gravity divided by area. So let's say we have the Earth. Here it is. This is my Earth. Okay. There's the center of the Earth. Now remember, around that Earth, we have our atmosphere. Here's our atmosphere. And that was a pretty poor circle. All right. Now, by gravity, gravity is pulling our atmosphere down. So, okay, if I'm standing right here on the Earth, okay, there's pressure being pulled down on me due to this gravity pulling down on the gas particles, right? And it's putting pressure on me, right? And it depends on how much gas is above me. Okay, so if I'm here on the surface, I have all of this gas above me pushing down, so the pressure is going to be greater. Right, now, what happens if I'm standing up here or I'm in an airplane up here? What happens to the pressure that's being put on me if I'm up in the atmosphere? Well, there's less gas above me, so the pressure is less. So as you increase in altitude, less mass of air is above you, which means there'll be less pressure. Now, what measures this atmospheric pressure? Well, we use a barometer. So a barometer actually will measure atmospheric pressure. And if you watch the weather, we have high pressure systems and low pressure systems. All right, and we're measuring that pressure using a barometer. Now, we need to be able to use some different units of pressure. And we'll use atmospheres, okay, which are ATMs. You'll see torr, which is an old English unit. Its abbreviation is torr. We'll use millimeters of mercury. And that's mmHg. That makes sense, millimeters of mercury. And we'll use the Pascal. Which is PA. And 1 Pascal is equal to 1 Newton per meter squared. Right, we'll use kilopascals, which is kPa. Okay, it's really the same unit, except we're adding this kilo to it. Right, now you need to be able to convert from all of these. All right, so I got to give you those conversions. So 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr. Which is equal to 101325 pascals, which is equal to 101.325 kilopascals. And you could probably figure this out. 1 atmosphere is actually equal to 76 centimeters of mercury. All right, so you just drop that, all right? But these are your conversions, all right? So you should be able to go, all right, you should be able to go from one unit to another just by setting up ratios. Okay. Just by setting up ratios. It's not a big deal. So, all right, if I want to know, I don't know, how many torr are in 2 atmospheres, well, 1 atmosphere would be 760 millimeters of mercury, or torr. I don't know what I said. If I want to know what 2 atmospheres is, okay, I just set up that ratio and cross multiply. This would be what, 1520 millimeters of mercury. Is that right? 760, 0. Yep, 1520. So you can just set up ratio and you can convert into these. So you need to be able to do that. And so those are units of pressure that we're going to be using. All right, so now when we're doing our gas calculations, there are 4 variables that we're going to be dealing with. Temperature, pressure, volume, and moles of gas. Temperature, pressure, volume, moles, temperature, pressure, volume, and moles of gas. And there are relationships between all of these. And these relationships are called the gas laws. First gas law I want to talk about is Boyle's law. And Boyle's law is an inverse relationship between pressure and volume. And in Boyle's law, temp and number of moles of gas are constant. So what this is saying is pressure increases, the volume of the gas decreases. Or as the volume increases, our pressure decreases. So our pressure has an inverse relationship with volume. Now, if you have an inverse relationship and you want a constant, okay, so if we rewrite this, P times V, okay, will equal a constant. So whenever I multiply this, I'm going to get the same number. All right, which means we can do this. P1V1 is equal to P2V2. Right, so now we have this inverse relationship, and we can actually do some math by changing pressures and volumes. Now, what does Boyle's law really say? So let's look at this guy. Okay, so inside my syringe, okay, I have a set number of gas particles. All right, now this syringe it's sealed, so nothing can come out. So I have a set number of gas particles, and I'm not going to change the temperature. Well, if I push down, if I increase my pressure, okay, the pressure inside there is going to increase, but my volume gets smaller. So I'm getting smaller and smaller and smaller volume. And vice versa. If I pull this out, I'm increasing my volume, which means the pressure produced by the gas inside is going to decrease. Now, what's actually happening in here? Well, remember, the pressure is actually being produced by hitting the sides of the container walls. So if I open up this volume and spread out that gas, what happens to the number of collisions inside there? Well, the number of collisions is going to decrease. If the number of collisions decrease because they're moving further and further and further apart, right, that means the pressure inside is going to decrease. Now, if I decrease my volume, the particles are going to hit the side of the container walls more often. And in that case, there are more collisions, which means we're going to get a higher pressure. Okay? And this is Boyle's law. Now, if we were to graph Boyle's law, pressure and volume, okay, at low volumes, we have high pressures. As we increase that volume, my pressure goes down. Right? So if we were to draw, or if we were to actually graph Boyle's law, we would get something like this. Okay. Now, there's a big numeric relationship here. So if we talk about this, let's say that right now, there's 1 atmosphere of pressure in there. Okay. If I was to half my volume, it actually doubles my pressure. So if I decrease it by half, my volume by half, I'm going to double my pressure. So this would have 2 atmospheres in there. Okay. Let's say that I double my volume, which means it would half my pressure. So now I would have a half an atmosphere of pressure in there. Okay. And that's what this equation is actually giving us. And this is called Boyle's law. second relationship that we're going to talk about is Charles' law. This is a direct relationship between temperature and volume. And in this one, pressure and number of moles are constant. So volume has a direct relationship with temperature. So if volume increases, temperature increases. If temperature increases, volume increases. So if it's a direct relationship and we divide those variables, we will get a constant. So V divided by T gives me a constant. So if V1, T1 equals a constant, V2, T2 has to equal that same constant. So I can rewrite this as V1, T1 equals V2, T2. And this is Charles' law. Now, what is Charles' law? Okay, you've seen this before. How many of you have ever cooked a marshmallow in a microwave? Okay, so if you know what a marshmallow is, right, this is sugar. Okay, this is sugar with just air pockets in here. Okay, if I put this marshmallow in the microwave, it heats up the gas in here. Well, the number of gas molecules is the same. The pressure is going to stay the same. So what happens here is my volume is going to increase. And if we put this in the microwave, okay, you can do it at home. Okay, you'll see the marshmallow get bigger and bigger and bigger. Okay, it's because as my temperature is increasing, the volume of this gas inside the marshmallow is increasing, and it makes it expand. So you can actually do this at home. Okay, it's pretty cool. You've probably seen that. So Charles also has a graph that you need to know. If we graph Charles' law, okay, you get something like this. You get this direct relationship. Now, Charles' law is how we initially calculated absolute zero. Oops. And here's how. So let's say that we have a tube. And this tube is closed at this end. Okay, so it's hollow. And inside we have a bead of oil, and which means this is a gas. Okay, so we got gas in here and it's trapped. Now, these particles in here are moving, and they're applying a pressure to the oil. Okay, if they're moving faster, if we increase the temperature of this, there's going to be more collisions, and the oil is going to move up. If we decrease the temperature, okay, these particles will be moving slower. Okay, they'll be hitting the oil less, and the oil will move this way. The slower the gas particles move, okay, the smaller the volume. If we get to absolute zero, at absolute zero, the particles are completely stopped. There is no motion. So that means the volume of gas would be zero at absolute zero. So with that idea, okay, Okay, so here's absolute zero down here. Okay, so here's my volume of zero. Okay, now in Kelvin, we can't get way down here towards absolute zero. All right. So what we do is we can measure the changes way up here. And this is a lab that you do. So we measure the changes of this right here, okay, up near room temperature and stuff. And then we can extrapolate back. Okay, we extrapolate backwards. Okay, when there is no volume, okay, that would be at negative 273 degrees Celsius, or 0 K. Right, so this is how we actually calculated where absolute zero was. Our third law is Gay-Lussac's law. And this is a direct relationship between pressure and temperature. And in this case, moles of gas is constant and volume is constant. All right, so this is a direct relationship between pressure, and temperature. Right? If it's a direct relationship, to get our constant, we divide. So P over T equals a constant. So that means we can get P1 over T1 equals P2 over T2. So if we increase our temperature, our pressure is going to go up as long as our volume is constant. Now that makes sense. Okay, so let's say we have a constant constant volume container. Let's say that we have 1, 2, 3, 4, 5 gas molecules in there. Okay, these are producing a pressure. Okay, so every time they hit the wall, they're going to produce a pressure. If we increase our temp, these particles are going to move faster. If they're moving faster, they're going to hit the side of the wall containers more often. If they're hitting the container walls more often, okay, they're going to produce a higher pressure. Okay. Let's talk about Avogadro's principle. If two samples of gas have same volume, same temperature, and same pressure, if both samples of gas have the same exact things, that tells us that they have the same number of gas particles in the samples. Same number of gas particles. So let's say we have two containers. Both of them are 4.0 liters. I don't know, in this one we have oxygen, and in this one we have carbon dioxide. We place both containers at 25 degrees Celsius. So that means the particles are moving the same speed. That's what that means. Okay. They have the same amount of space to travel. Let's say both are producing 2.5 atmospheres. Well, if they are moving in the same space, they're moving at the same speed, and they're producing the same pressure, okay, they're going to have the same number of collisions happening on both sides. Well, if we know that's true, they're having the same number of collisions, that means they have to have the same number of particles, gas particles inside. Okay, and then that's Avogadro's principle. Now, he also said this. There is a direct relationship between moles of gas and volume. Okay, so V is directly proportional to N, which is moles. So V divided by N would be a constant. So we could write V1 over N1 equals V2 over N2. Now, this one's pretty easy to see. So let's say I have a balloon, all right, and I go and I blow up the balloon a little bit, okay? I have just put some gas particles inside that balloon and it has a volume. Right? Now, if I take that same balloon and I go and put more gas particles in there, what's going to happen to the volume? It's going to get bigger, okay? So that's part of Avogadro's principle. Now, this brings us to what's called the combined gas law. The combined gas law takes Boyle's law, Charles' law, and Gay-Lussac's law, so the inverse relationship between pressure and volume, the direct relationship between volume and temperature, and the direct relationship between pressure and temperature. We're holding moles constant. Okay, so we can put all of these together. Okay. So pressure times volume is actually in a direct relationship with temperature. So that means P times V over T is equal to a constant. So if I have P1 V1 over T1 equaling a constant, P2 V2 over T2 has to equal the same constant. So that means we can say P1 V1 over T1 equals P2 V2 over T2. And this is what's called the combined gas law. Now, in the combined gas law, you got to remember, okay, we can't vary the number of moles of gas. The amount of gas has to be constant. Well, is there an equation that relates all of these? And that's yes. Okay. Now, the combined gas law, okay, from the combined gas law, we can actually get what's called our ideal gas law. And that's going to put it all together. Okay. And we get PV equals nRT. Okay, so this is pressure. That would be volume. This is moles of gas. This is what's called the universal gas constant. All right, and this is temperature. Now, in the lab that we're doing, we're trying to calculate this gas constant. Okay, that's what we're doing in the lab. Now, you need to know what the gas constants are. There are three you need to know. 0.08206 liter dot atmospheres moles dot Kelvin. Okay, and another way you'll see this unit is liter atmospheres mole -1 Kelvin -1. Second gas constant is 8.314 joules per mole dot K. And this is joules mole -1 K -1. And our third one is 62.36 liter dot torr dot mole or over mole Kelvin. Liter torrs mole -1 K -1. Now, which one do you use in PV equals nRT? All right, well, the gas constant used is dependent or determined by the pressure unit you are in. Okay. So if you're in atmospheres, we have to use this one. If we're in kilopascals, we need to use this one. If you're in torr, you have to use this one. Now, when we look at PV equals nRT, okay, it doesn't matter what pressure is. Okay, it can be in any pressure. Volume has to be in liters. Why? Because our constants are in liters. Our temperature has to be in Kelvin. Why? Because these gas constants are in Kelvin. All right, so you have to be in Kelvin and you have to be in liters. All right, so I think that's where we're going to stop. All right, we'll do some practice with this next time. All right, and we will keep going with gas laws next time. Have a good afternoon.